One of the quieter legacies of the Korean War was the moment when chemical preservation replaced patience as the default answer to wood decay. Faced with emergency construction in a cold, wet theater, bridges, barracks, supply depots, the United States and its allies leaned heavily on pressure-treated lumber and synthetic preservatives. These solutions worked, but they also narrowed institutional memory. Within a generation, many older methods of preventing rot were dismissed as primitive or inefficient, not because they failed, but because they took time, observation, and local knowledge. What most people never learn is that for thousands of years before industrial chemistry, woodworkers routinely built structures that survived centuries in harsh climates using no chemical treatment at all. Understanding how they did it requires stepping away from modern assumptions and looking closely at decisions shaped by scarcity, war, and long experience. Rot was treated as a structural problem long before it was treated as a chemical one. Traditional woodworkers did not think of rot as an infection to be poisoned. They understood it as a predictable outcome of moisture, stagnation, and poor airflow. Long before laboratory science explained fungi and decay, builders recognized cause and effect through failure. Timber that stayed wet rotted. Timber that dried quickly endured. Everything else followed from that observation. This mindset mirrors how pre-industrial militaries approached logistics and shelter. Armies in East Asia and Europe learned through bitter experience that poorly sited camps bred disease and collapse. The same reasoning applied to buildings. Prevention focused on controlling environment rather than altering material chemistry. Wood was left chemically unchanged but structurally protected. Choosing the right tree mattered more than any later intervention. Species selection was the first line of defense against rot. Oak, chestnut, larch, cedar, and cypress were favored not for tradition, but for their cellular structure and natural extractives. These woods contain oils, tannins, or resins that slow fungal growth and repel insects. Importantly, these properties are inherent, not applied. Equally critical was how the tree was grown. Slow-grown timber with tight growth rings resists moisture penetration more effectively than fast-grown plantation wood. Older foresters understood this intuitively. In wartime contexts, including Korea, this knowledge was often ignored in favor of volume and speed, leading to greater dependence on chemical treatments to compensate for weaker material. Seasoning was a long, deliberate process, not a step to be rushed. Air drying was not merely about reducing moisture content. It allowed wood to reach equilibrium with its intended environment. Beams were stacked with spacers to encourage airflow and kept off the ground to prevent ground moisture absorption. This process could take years, and it was adjusted for climate, thickness, and species. In military terms, this was a logistics decision. You stockpiled material long before you needed it. Post-war industrial practices inverted that logic. Kiln drying accelerated production, but introduced internal stresses that later expressed themselves as cracking and joint failure. Traditional builders accepted delay in exchange for stability. Design choices made water the enemy, not the wood. Historic structures were designed to shed water aggressively. Roof pitches were steep, overhangs were deep, walls were layered to drain and dry rather than sealed airtight. Foundations lifted wood away from soil contact, often using stone, brick, or compacted earth, that wicked moisture away rather than trapping it. These decisions, you see, were not just about aesthetics. They were informed by repeated observations of failure. Military engineers learned similar lessons when constructing fortifications and supply buildings in monsoon climates. Structures that breathed survived, while those that trapped moisture failed quickly, regardless of material strength. Fire and heat were employed as preservative tools, not merely for shaping. Charring wood surfaces was a widespread practice. Light surface charring closes pores, reduces moisture absorption, and creates an inhospitable environment for fungi and insects. This technique appears across cultures, from Japanese timber construction to European fencing and shipbuilding. Heat was also used more subtly. Some timbers were dried near hearths or smokehouses, where creosote-like compounds from smoke deposited into the wood. Now, this wasn't chemical treatment in the modern sense, but it altered surface chemistry through exposure rather than application. These methods were slow, local, and required attention, but they worked. Traditional builders paid close attention to how wood was oriented. Heartwood faced outward. Sapwood, which decays faster, was placed where it could dry or be replaced. End grain was protected from direct exposure, recognizing that it absorbs moisture more readily than face grain. This awareness extended to site selection. Buildings were placed on slopes rather than low ground. Drainage paths were maintained deliberately. In military campaigns, camps placed without regard for drainage suffered predictable consequences. Civilian builders absorbed the same lesson over generations. Maintenance was assumed, not deferred. Old structures survived because they were maintained as part of their life cycle. Roofs were inspected. Boards were replaced individually. Failure was localized and visible. This approach mirrors how pre-modern armies managed equipment. Items were repaired continuously because replacement was uncertain. The post-Korean War building economy shifted toward disposability. Maintenance became an afterthought, and when paired with sealed systems, decay progressed invisibly. Traditional methods relied on openness and access, making decay slow and detectable. The Korean War intensified a broader trend towards standardization and chemical reliance. Treated lumber allowed rapid deployment in hostile climates without waiting for seasoning or ideal species. This was a rational decision under wartime pressure. The problem came later, when emergency practices became permanent norms. As with many military innovations, context was, lost. What was designed for short-term survival became, standard for long-term construction. The result was a generation of buildings dependent on chemical systems that require perfect installation and ongoing replacement. Traditional rot prevention teaches, restraint. It really emphasizes observation over intervention and design over treatment. For those concerned with resilience, whether in civilian life or, say, contingency planning, the lesson is clear. Systems that rely on material properties and environmental control tend to fail more gracefully than those dependent on external inputs. This is not by any means a rejection of modern science. Rather, it's a reminder that older methods evolved under constraints quite similar to those faced in disrupted supply chains and austere conditions. They were shaped by necessity, not by nostalgia. The story of how woodworkers prevented rot without chemicals is also in a way a story about how knowledge is lost when conditions change too quickly. Wars like Korea accelerate innovation but at the same time erase memory. When we forget why older structures endured, we end up repeating the same mistakes under different names. Understanding these practices is not about returning to the past, it is instead about recovering options. So, if this kind of careful, historically grounded analysis matters to you, do subscribe to the channel and share this video with others who value depth, context, and lessons that endure beyond a single generation.